I want to call on the stage Mikio Braun from Zalando.
Thanks for the nice introduction. Okay, so I assume you all know Zalando, but you're probably not aware how big Zalando has actually become. So these are the official numbers from last year. So we're currently serving 15 countries. We have 7 locations, 7 offices, right? So Berlin, Helsinki, Dublin, Dortmund, and a few others, Hamburg. And we had almost 3.6 billion in revenue in 2016 and 12,000 employees, right? So we're not a startup anymore. Actually, we are running into like really enterprise kind of scaling problems, which makes things, of course, also very interesting, right? Because data science is always a bit more agile, a bit more, you want to get your hands on the data, and so that's the question, how we can keep doing this while the company gets so large. It's very interesting. Okay, so I'm running a few teams which do the search backend, right? So if you think about so if this is like a mini version of Zalando, so down here is the customer and this is his screen, right? And then for search, actually, so he looks for stuff like black t-shirts, and then this somehow ends up in search, and search produces the results, and then the customer buys something, and then it gets delivered, and then everybody's happy, right? So this is sort of the customer-facing part, but if you look in the back, so actually there's like the factories which build the articles. Also, I think build is not the right word, you know what I mean? And then they get up in the warehouses, and then we get the data for the articles, and that somehow that has to end up in search so that we also have nice results, right? And that's already, like the first problem is, so all of our search is sort of based on the data we get from the manufacturers, but this might not actually be in the right language or have the right terms, which is what the customer is talking about, right? So that's already a first area where AI or machine learning or data analysis, how you want to call it, can be used. And then, of course, another point is, so the order in which you want to sort the results, right? So we have about 300,000 articles online every day. And then if you search for black t-shirts, so which are the black t-shirts that the customer is actually interested in, which brands is he interested in, what styles, and so on. This is also something which you try to sort of learn automatically from the logs, because nobody can actually, with so many articles and so many updates each day, nobody can do that by hand. Okay, but this is sort of where I come from. Before I joined Zalando 2 years ago, I was a machine learning researcher at TU Berlin for about 11 years. So now I'm sort of trying to bring both of these worlds together. Okay, and today, so what I want to talk about is 2 deep learning applications that we did at Zalando, not in the context of search, unfortunately, there are also papers on that, so if you want to have more details, you can look these up. And this is sort of, I mean, most of this, of course, is driven by standard technology, standard search engines, recommendation is done with collaborative filtering, all of that. But there are interesting corner cases, which I try to talk about, where this new approaches really are quite promising. Okay, deep learning. So I want to do like a mini introduction of deep learning for images. Okay, so one of the academic tasks that this whole computer vision community has been working on is image recognition, right? So there's some data sets. So this is from the CFAR. That's like how to say? So the academic community puts work into constructing these data sets, and then they publish them each year. So they also try to update them to make them more challenging. And then everybody benchmarks himself against these data sets, right? So these data sets are pretty important because they also try to define, like, what is the next difficult problem for computer vision, right? So once we've solved everything, once the thing is good, they say, okay, let's make it a bit more complicated. Right, so in one of the simplest versions, you have these rather small images, which they scrape from the net, and then you have a number, like hundreds of these categories. So this is an automobile, bird, cat, and so on. And the task is, of course, so you show this picture, and then the computer is supposed to tell you what's on the picture, right? But it's very simple because there's just one thing on the picture, and the pictures all have the same size. A bit more complicated is this kind of stuff, where you have a real picture, and then you have annotated objects which are on the picture. So you have chairs, you know, this is what is it actually? Conference room, living room. So you have a number of chairs, some plants, and so on, and you have different, like potted plant, truncated and occluded. So you have a plant somewhere in the back which you cannot really see, okay? And this is also a class. And then the task gets, so compared to this, right? So this is sort of rather easy, let's say. So at some point they solve this. Let's say, okay, let's try to make it more complicated, but actually you don't know where the objects are, you don't know how many of them are, some of them are overlapping and so on, right? And they try to use these things, which is more classical statistical methods, right? So if you have enough data, you can try to figure out, okay, which kind of color distribution, whatever, helps you, what kind of shapes. So they try to explicitly find shapes and points and so on. And they did this for like a long time, decades. But then recently, with the fast computers we have nowadays, they figured out that if they use the deep learning technology, which has actually been sort of already developed in the 80s, they could now learn on millions of pictures in reasonable time and outperform everything they had before, right? And this is actually the interesting thing, one of the interesting things about deep learning. Okay. So but how does it work, right? So it's not magic. It's still just software running on a computer. But actually, most of what they use, the architectures they use for deep learning, they're very much inspired by what we know about the visual system. So this is this is the brain, okay, and these are the eyes, and this is what you look at, and then there's an area where where the pictures overlap, and this is where we sort of try to recognize objects, right? And then we know a lot about, especially mostly about the early stages. So what kind of signal processing actually happens in the eyes, right? What kind of signals do we get down here? And then it somehow ends up in the primary visual cortex. And after that, we don't actually know what happens, right? So after that, it gets pretty complicated. And the interesting thing about this visual system is that we're able to recognize objects, although a lot of different things can change, right? So lighting can change. So if you met your friend in sunlight and then you meet him again at night, you would still recognize him, okay? Also perspective, color, size, deformation. So, I mean, animals, if you think about it, right, they're moving all the time. And for some reason, it seems it has been important that we are still able to recognize this, right? So maybe evolutional pressure, I don't know. So when you're in the jungle and then there's a tiger behind the tree, you still need to recognize him. Okay. So, but now sort of what the kind of architectures we're using nowadays for this image recognition, what we call deep learning, they are very much modeled like this, right? So they look something like this. So this is not the robot with the deep learning, no, this is the input image, okay? And then there are different layers which perform different kinds of data of analysis, or which potentially can perform different kinds of image processing, right? And this is a bit modeled after this. So the first layers, they are sort of doing the kind of edge detection which happens directly in the eyes and so on, right? Yeah. And then, so you have, actually what you have is you take the input image and then you have layers which have different architecture setups. So you have stuff which computes convolutions, which is more like small image filtering, image processing. You have a subsampling, which sort of takes a small part of the image and then tries, so if somewhere in this image you have an interesting signal, it takes that, right? So that way you're getting position independent and so on. And then in the very end you have what is called fully connected down here. So you have something like a very general network which can learn all kind of things. Okay. Right, so this convolution, the thing is actually, like mathematically what you're doing is you're doing a small filter operation, so just like in Photoshop, right? So you can, if you ever played with that, you have these edge detectors in Photoshop or these enhancers or so. So this is actually what happens. But the thing is, so you only give the architecture and then the network can learn the right kind of filtering by itself from the data, right? But usually what you learn is some kind of edge detection, but this means if you have like the picture, like a dark picture and a brighter picture, and then if you do the edge detection, then you get the same response after that. So, right, so you get independence from lighting, which is exactly. And then there's this pooling. What I already try to say is, so if you have like in the response window, you have a response in the upper left or in the upper right, so it picks like the maximum response in the window, and then that way you also get position independence. Okay, so this is sort of deep learning for images in a nutshell. So how are we using that at Zalando? And we're using that for a thing which we call the fashion DNA. Okay, and we're using that in the context of recommendation, right? So in recommendation, you sort of have this is again the user who looks at articles, looks pretty happy. and you're tracking everything that he's looking at. And then the question is, like, if you have this shoe, what other similar items can I show to this user, right? So this is, besides search, that's the second most important way of helping the user navigate this large assortment that we have. And there are different ways to do this. And usually if you have a lot of logs, and luckily for Zalando and like in Germany, we have so many customers, it's not a problem. So even if there's a new item, we usually have, like after a few hours, we have enough data that we know really how this item relates to other items, and we can make good recommendations. But there are some use cases, like smaller countries where we don't have that much traffic, or the Lounge, right? So you know, Lounge is a website also which belongs to Zalando, where you have these special offers, and usually they sell out very quickly, right? So you get an email at 7. So has anyone shopped with the Lounge? Okay, not that many. You should try it. You know, you register, you get an email, and then you get like, oh, just today we have this offer of shoes, and then, so yeah. Anyway, yes, but the problem is, right, from a recommendation perspective, is then the hottest items, they're just sold out in half an hour, and you don't really have any information. So how do you make recommendations on that? Right, and then the classical response to that is you can do something which is called content-based recommendations. So you try to recommend items based on like the data that you have. So you know you have a brown shoe, you recommend other brown shoes, right? So that way, that's pretty simple. But the problem, again, as I said, you remember the big picture in the beginning with the factory, so the data that we get actually might not be ideal for this, so you might want to use a data-driven approach to learn that kind of similarity. And this is exactly what our research lab did with this fashion DNA, right? So the idea is, now it gets a bit, so this is the link to the paper. So the idea is sort of you train so what you're doing is you're training this convolutional neural network. So the big thing, which you would normally use for image recognition, but now you're using like the outcome of, so this box here, this is like the big network which I had on the slide before with the many, many layers, okay? And then like on the output of that, what you do is you're using the response you get here, and you're trying to predict the user article by probability. So this sort of tells you which user has bought which item, and you're trying to predict this. And this is now the nice thing about deep learning, right? So you can just combine these different pieces of architecture. So you can take a network which you would use for image recognition, and then add something on top which does normal predictions, right? And then you can train the whole thing, and you will get like some kind of image recognition, but which features which are tailored towards recommendation, right? And recommendation means similar items. So what we get here in the end is a representation of the articles, which is sort of optimized towards what users think is similar, and that is what we call the fashion DNA. And then you can throw all of this away and just use this as a deep learning kind of representation of what is really interesting about articles. Okay, and then if you do this, this is a big picture, so I was afraid it would load slower. Now if you use this kind of similarity and then embed all your data, this is sort of the similarities that you get. So here you have all these trousers, black shirts, more like colorful dresses and so on, and the picture is much, much bigger. So you can find this also in the paper. Right, and that way, so this is one of the examples, right? So it's like a common problem, and there are many algorithms for this. There are some corner cases where it's really not that easy to do because you don't have a lot of data, but you can use deep learning, right? And the kind of understanding for the article data that you get from that to automatically get representations you can, for example, then use for recommendation, also for other things, so maybe also for search. Okay, so the other example I want to give you is dealing with user histories, right? I mean, so I think this is maybe one of the most important kinds of data you always have to deal with, because you always have all this user interaction, you want to make something, you want to use this data to optimize. Okay, so this is now a paper from the Zalando ad tech lab. So they worked, for example, on retargeting in Hamburg. And the problem they face is, so they want to figure out when customers are most closely to actually buying something, so that because they think this is the best way to show them some new ads, right? So if you because like for them, just showing an ad has a certain cost, they want to find the right moment when the user is like most interested in getting some ads. And the classical way to do that is sort of you have these event logs, so the user clicked on something, viewed a product, put something in the cart, and so on. and then he wants to order, and that is the point when you want to show him that stuff, right? So traditionally, or like before, they used the classical approach, which you would do, so you compute tons of features on your data, and you use the standard machine learning methods, and that actually worked quite well. But they said the problem here is you have to do all this hand tuning. So if something changes, you have to go through this whole pipeline again, and that takes that's just a lot of manual work, right? So they said maybe you can use deep learning so that it automatically understands the data and then helps us perform better. That was a setup, right? So what kind of, and the type of neural network, so let me try to briefly explain the type of neural networks we're using there. But first, so what is it actually that we want to compute from the data, right? So the approach I usually try to make is not just put something together and then hope for the best, but actually try to get an understanding of what is the kind of data analysis that you want to have, and then build deep learning architectures which are in principle able to compute this, and then throw the data at it and see what happens, right? So if you build a deep learning network, but it cannot actually compute the kind of thing you think is useful, then there's no point. Okay, and usually what you do, so here up again is the customer history, article views, add to cart, article view, catalog view, and then purchase, right? And then usually what you do, you compute simple time-based features, like, okay, over the past week, what was the favorite brand? What was the last time since a cart event, right? So if you think about it, actually, in order to buy something, you have to put it in your cart. So putting something into your cart is like highly indicative of that you actually buy something. So one of the features you probably want to work is, so when was the last time you put something in your cart? And yes. And so the classical approach is you compute like thousands of these things, right? What was the favorite brand over the last hour, last week, last day, and so on. And then you let a machine learning algorithm automatically pick the right features. But the deep learning way to that is using recurrent neural networks. And the way this actually works is, so the architecture looks a bit like something like this. So this is the input, this would be the events, right? And now, so each point here actually is like a full layer in the picture before. So it's not like, it's a bit hard to draw. So that's why, so this is not just one input, but this is actually like a full node which does some computation. So this is the input, the event, and this is the output that you're looking at. So this would be purchase, yes, no. This would be the event. And then what you, and so from here to here, you sort of have a normal neural network. But what you do is you also take part of the eternal state from the previous timestamp and then put it then to the next timestamp. Okay? And then that way, for example, if you want to compute the previous brand, you could have like one. So in principle, so this is not what the neural network, but like conceptually, it could be that you have in this internal state, you somehow store the brand the guy looked at, and then you add that to the current with a certain factor, and you take the current brand with a smaller factor, and that way you you're averaging over time and counting how much the different brands were, right? So this is how it could work. So let's throw some data at it, and then it works. And actually, so this is like the simplest version, where you always put a certain amount of the old data to the next level, but there are more complicated things, especially this long short-term memory, which has more ways of actually picking like which data to use. But in the end, it's all this kind of deep learning, and it's all trained in the same way, just using the data and trying to minimize the error. Okay. And now what they got? So this is a lot of data here. So down here, this is how well the thing performed for logistic regression is the old version, and then RNNs, this is the new thing, and actually it performed better, right? So the interesting thing is, so before they had this thing where you data scientists would have to work on this for a month or so, hand tuning everything, and now they use this deep learning approach, which of course is also very computationally expensive, but they directly were able to even get a little bit better performance. And then if you look at these, so this is sort of this internal representation that goes from point to point. And down here is this predicted probability that you would order. And down here are these events. So what it actually does is it looks a lot of cart events, so this is not a surprise, but you can see how the internal state sort of changes based on whether the process goes up or down. Okay. So, yeah. So in summary, so I tried to tell you like two applications. So I think like a lot of this stuff that we're dealing with, there you would solve with like standard methods, right? Also like in Johannes' talk. So the simple methods usually already work quite well. but there are very interesting corner cases which are very hard to do. And then if you use deep learning, you can actually sort of use the automatic understanding of the data that you get, and you can get away with not having to do all this data cleaning and handcrafting of features. Okay, thank you very much.
We have time for 2 very quick questions.
Where does your team spend actually most of the time with? Is it actually model development or something else?
Yes, model. I mean, so I think the hard part is always getting the data, but then you actually spend most of your time on, and then setting up this whole infrastructure that you can actually iterate on the models quickly, but once you are there, you can actually spend most of your time there. Right, and then it's this whole, so you create something, you have to run an A/B test, so there's a lot of, this whole process is, it's a big process, let's say. One more question, yes. No, so this is, let me think. No, this is sort of, I think, for all users. So you have to check the paper, I'm not sure. But no, the raw data that you get is really just the raw events. So just a timestamp and then some encoding of the event type. This is all the input that you get. And I think this is, but then combined for all users, and you use this to train sort of a model, which can then, if you have a user history, predict whether or not what the buy probability is.
So that was it. Thank you so much, Mikio.
Yeah, thank you very much.
Thank you so much, Zalando.